Consider a spherical object now, okay? And let's say it is moving through a fluid, could be a liquid or a gas. Fine. Assume it is moving to the right. Now, you all must have experienced this in daily life also. Suppose you are riding a bike and you are moving towards east. Do you experience air resistance or not? You will definitely experience, okay? You will experience force from surrounding air molecules, okay? Suppose you are riding towards east. In which direction do you experience force from the surrounding air? If you are riding towards east, in which direction do you experience force from the surrounding air molecules? From everyday experience. Okay. If you're riding in the forward direction towards east, air molecules will be hitting you in the opposite direction. Okay. So you will experience the air resistance in the opposite direction, that is towards west. Fine. And you must have experienced this also. The faster you ride through air, greater the air resistance you experience. Fine. So basically, the amount of air resistance you experience, the amount of force due to air that you experience depends on your relative velocity with respect to air. Now, sometimes without moving also you can experience air resistance. That is when air is flowing. Okay, you are at rest, but if air is flowing, you can experience air resistance. Fine. I mean, you can experience force due to air. That is nothing but a viscous force. The air resistance that you feel or the air drag that you feel is nothing but viscous force. So the amount of viscous force acting and the direction in which it acts depends on the relative velocity between the object and the fluid, be it air or any other liquid. Okay, be it gases or liquids. Viscous force acting depends on the relative velocity between the object and the fluid through which it is moving. Okay. So consider a sphere moving through a fluid like this. Let's say it is moving to the right. So its velocity is towards right. Now, if velocity is towards right relative to the fluid, okay, velocity is towards right, then it will experience a viscous force towards left. Okay. The drag force acting on it will be acting towards left. Okay. FV stands for viscous force or the drag force or resistive force. You can call it any of these. Can you guess the factors on which the magnitude of this force depends? How much air resistance or how much viscous force acts on a sphere moving through a fluid? What factors does it depend on? I'll give you a minute. Give your answers. Okay. The viscous force or the resistive force experienced by the object, which is a sphere in this case, definitely depends on the speed with which it is moving. So I'll write it down here. Viscous force depends on speed. What speed is this? Remember, they don't mention this in many books. It's the speed of the object relative to the medium in which it is moving. Okay? Be it air or water or any fluid. Relative to that fluid, you have to take the speed. Okay? The other factors on which it depends are obviously one factor is the size of the sphere. Bigger the sphere, greater the number of molecules hitting it in the opposite direction, greater the amount of viscous force it experiences. So size of a sphere is expressed in terms of its radius, right? So the amount of viscous force experienced by the sphere depends on how fast it is moving through the fluid, and it also depends on the size of the sphere, that is its radius. And definitely it should depend on the properties of the fluid as well. Not every fluid exerts the same amount of resistive force for a given speed and size. So it depends on viscosity of the fluid as well. Fine. So this scientist named Stokes, okay, Stokes, I'll find out. He performed experiments and concluded that these are the factors: speed, radius, and viscosity of the fluid are the factors on which the viscous force experienced by a sphere depends. Okay. Now, using dimensional analysis, derive how viscous force depends on these three factors. Can one of you tell me what we mean by using dimensional analysis to derive a relation between physical quantities? What are we supposed to do? If you want to relate physical quantities using dimensional analysis, what you have to do is write the dimensions of one quantity. You want to express viscous force in terms of the other quantities, right? So the dimensions of viscous force, we'll assume they are proportional to dimensions of speed to the power of A, radius to the power of B, coefficient of viscosity to the power of C. We will get the exponents A, B, and C by balancing the dimensions on both sides. Okay, do this all of you. I'll give you 2 minutes. Yeah, just a clarification. The name of the scientist is Stokes. Fine. Stokes found that viscous force acting on a sphere depends on speed, radius, and coefficient of viscosity. So do this all of you. Right. Viscous force is just a force. Dimensional formula is mlt per minus 2. Velocity lt power minus 1 to the power of A. Radius is L to the power of B. Coefficient of viscosity we had derived in the last class. M L power minus 1 T power. How much was it? Minus 1. Is that correct for coefficient of viscosity? Okay, anyway, I remember the unit Pascal second. So force per unit area multiplied with time. So ml power minus 1, T power minus 1. That is correct only. From the unit, I am quickly getting the dimensions. Right. Now we just have to compare the powers of each quantity on the left hand side and right hand side. Left hand side, the power of m is 1. Right hand side, it is c. So c is equal to 1. Next, the power of L on the left hand side is 1. Right side, it is A plus B minus C. C is 1 already. So that means A plus B is 2. Okay. Then the power of T, if you consider, minus 2 is equal to minus A minus C. C is 1. So minus A becomes minus 1. That means A is 1. And if A is 1, that makes B also equal to 1. Therefore, A, B, C are all equal to 1. So what we can say is that the viscous force acting on a sphere is proportional to eta r v. Okay. Now, there may be a dimensionless proportionality constant also. So we write viscous force is equal to some constant, unknown constant k multiplied with eta r v. And Stokes performed experiments and experimentally determined that this proportionality constant is 6 pi. Okay. Therefore, viscous force acting on a sphere is 6 pi eta rv. If you treat this as a vector, if you write it in vector form, okay, as a vector, the force will be opposite to the direction in which the object is moving through the fluid. So minus 6 pi eta r v vector. So if you know the exact direction of velocity, opposite to it will be the direction of the viscous force. And remember, V here, okay, as I said, they don't usually mention it in books. V here is the relative velocity of the sphere through the fluid. Okay. Let's solve one problem based on this. consider this situation itself. Ignore gravity. Okay, next case will include gravity also. Ignore gravity. Let's say there is a viscous fluid. Coefficient of viscosity is given to you eta, and assume a sphere is set into motion with initial speed u. Fine. Coefficient of viscosity is given. The sphere's density is rho and its radius is r. Okay. So we give it an initial speed u and release it. Can one of you describe what is going to happen? No gravity. If we give the sphere some velocity and release, what is going to happen? We are releasing it in a viscous fluid.
So it will stop after some.
Yeah, it will gradually slow down due to the viscous force and stop. Okay. Will the viscous force acting on it be a constant force or a variable force?
Variable.
Variable. Why?
So because the velocity is changing.
Good. Viscous force depends on the speed with which the object is moving through the fluid. Now, we know that the speed is going to reduce, so the viscous force will also reduce. Okay, so first, write an expression for viscous force acting on it at a random instant. What do I mean by random instant? See, initially its speed is u, but later its speed won't be u. So consider some random speed v. Okay. Assuming the speed is v, write the expression for viscous force. You already know the expression. Okay. Now from viscous force expression, derive the expression for acceleration. Don't forget to put a negative sign because acceleration will be opposite to velocity. Viscous force itself is opposite to velocity. So the resulting acceleration will be opposite to velocity. Obviously, this will be a variable acceleration. And if acceleration is variable, you can't apply equations of kinematics. But you can apply basic definitions. Like you can apply acceleration is dv by dt. Okay. You can also apply acceleration is v dv by ds. If you want to relate acceleration, velocity, and displacement, you can use a is equal to v dv by ds, provided it moves in one direction only. This object is definitely going to move only in one direction. We gave velocity to the right, so viscous force will act to the left. So it will slow down, and stop, but it will keep moving in the same direction always. Why will it change direction? Okay, acceleration is exactly opposite to velocity, so it will only slow down. There's no perpendicular component of acceleration. There's no radial acceleration for it to deviate from its path. So it will move in a straight line only. You can use any of these. So what I want you to do is using both of them. Okay. Using a is equal to dv by dt, derive its velocity as a function of time. Next, using a is equal to v dv by ds, derive its velocity as a function of distance covered. Since it's going to move in the same direction, distance and magnitude of displacement are the same. So you can call it displacement if you want, or call it distance. Okay, do this both of you. I'll give you 4 minutes. Density is given, radius of the sphere is given. From density radius, you can get the mass that will be needed in expressing acceleration. Or if you want, you just write m, not an issue. At the end, you can substitute mass is density into volume. You can assume it as m if you want. Coefficient of viscosity is given, initial velocity is given, right? Do this. Okay. At a random instant, if we assume the speed of the sphere is v, then the viscous force acting on it directly from Stokes' law, you can say 6 pi eta rv, including direction. If you write, it will be with minus. Now, this force itself will be the net force acting on it. No other force acts on it. Should be equal to mass multiplied with acceleration. Therefore, acceleration will be, since acceleration is definitely opposite to velocity, we'll take it with a negative sign, minus 6 pi eta rv divided by m. Okay. So acceleration depends on how fast the object is moving. Fine. Next, you need velocity as a function of time. Have any of you done this? Third part. See this 6 pi eta r by m. I'll just call this k, okay, constant. So you can take acceleration as minus kv. Okay, minus sign is important. You don't merge it in the constant. Okay. If you want velocity as a function of time, you equate this to dv by dt. Okay. Can any of you tell me how to proceed after this? We need v in terms of t. How to proceed?
So we can integrate on both sides.
Directly like this you'll integrate, or do you need to make any adjustments?
So we can send dt that side and we can integrate.
You should keep t terms on one side and v terms on the other side. Okay. Only then you can integrate. Fine. So minus k integral dt becomes t. Limits are from 0 to t is equal to, what is integral 1 by v dv? Or integral 1 by x dx? It is ln x. Okay, natural log. So here it becomes ln of v from initial velocity u to random velocity v at some instant. Okay. Therefore, left hand side will be minus kt, where k is that constant 6 pi eta r divided by m. You can substitute it later. Is equal to ln v minus ln u. Ln a minus ln b is ln a by b. So this becomes ln of v divided by u. Okay. Ln means log to the base of e. Now send e this side. It means v divided by u is equal to e to the power of minus kt. Okay. That means v, the velocity at any instant, is initial velocity u multiplied with e to the power of minus kt. Okay, interesting result. Since the power of e is negative, we say that velocity decreases exponentially with time. Okay, as t increases, the velocity goes on decreasing. Initially, when you substitute t as 0, e to the power of 0 is 1. So v becomes equal to u. So initial velocity is u, but as time passes, as t increases, the v value keeps coming down. Okay. And when does this become 0? Actually, for the exponential function to become 0, can you guess when will this become 0?
So when t is tending to infinity.
When t tends to infinity. Correct. Okay. So theoretically, the object never comes to rest. But its speed will keep on decreasing. Now, if speed is decreasing, how come it doesn't come to rest? Because if speed is decreasing, the opposing force is also decreasing. So the rate at which it slows down decreases. Initially, it will slow down very rapidly. Okay, sudden fall in speed will be there. But then the rate at which it slows down will decrease, decrease, decrease. It will never stop theoretically. Okay. So if you draw the graph of its speed as a function of time, at t equal to 0, the velocity was u or the speed was u, and it decreases exponentially like this. Okay. As t tends to infinity, the graph will tend to 0. Okay, so you should not make it touch the x-axis. The graph will be like this. So they may ask you questions like in some time, let's say t naught, velocity becomes half. In another time t naught, what happens? Such questions can be asked. Okay, but remember, under the influence of viscous force, only viscous force. We didn't consider gravity or any other force in this case. Under the influence of viscous force, which is directly proportional to speed of the object, the speed decreases exponentially. Okay, you can even tell its speed at any time by using this equation. Okay, then the last part of the question, velocity as a function of displacement. We got acceleration as minus kv. Now, if you want it in terms of displacement, you just equate it to v dv by ds. That's all. V gets cancelled. You get dv is equal to minus k times ds. This is much easier to solve. Integral dv is v. Substitute limits initial to final is equal to minus k. Integral ds is s. Substitute limits initial displacement is 0. Final displacement, let it be s itself. So right hand side becomes minus k into s. Left hand side is v minus u. So v is equal to u minus ks. Now why is this interesting? You can tell the distance in which it is going to stop. Okay. For v to become 0, it means u should become equal to ks. That means s should become equal to u divided by k. Within that distance, it is going to stop. But to cover that distance, it takes infinite time. Okay. It'll be slowing down, slowing down, slowing down. It will never cover that distance basically. But if it covers that much distance, it is going to stop. Anyway, see, the purpose is not to remember these results or something, but based on the expression for force that you get, how to tell other things about the object. Okay, that is what we are learning. From force, we get acceleration. From acceleration, we can relate acceleration to velocity and time if you want, or you can also relate acceleration to velocity and position if you want, both of which we have done. Okay. So basically, this is what is Stokes' law. Viscous force acting on a sphere. Okay, as a vector, if you take, it will be minus 6 pi eta rv. Okay, that 6 pi constant was experimentally determined. Okay, based on this expression for viscous force acting on a sphere, we can derive an expression for something called terminal velocity. Vt. Last class also we talked very briefly about something called terminal velocity. Basically, when an object is falling down, the viscous force on it increases. Okay, and at some position, the force pulling it down, which is gravity, gets balanced by the viscous force. When gravity gets balanced by viscous force, net force on the object becomes zero. After that, its velocity won't increase. Basically, this is the idea behind the use of a parachute. Okay, when a skydiver or someone jumps off and opens the parachute, basically what happens, parachute, because it has a large area, the air molecules hitting the parachute from below, parachute will be falling down, no? Roughly it looks like this. This is more like a balloon. Anyway, let's say there is a person here. Yeah. So person coming down using the parachute. Parachute will be going down along with the person. Now air molecules will be hitting the parachute in the upward direction. So air resistance will act in the upward direction. That is what is viscous force. Gravity will be acting in the downward direction. So as the uh, speed increases, speed of the skydiver increases, at some speed, the viscous force due to air balances the weight. When the viscous force balances weight, net force on the parachute plus the diver becomes zero. From then onwards, the diver will move with a constant speed. And that speed will be so low that with that speed, even if the person hits the ground, it is not harmful. Okay. So that speed, that final speed is what we call as terminal velocity. Let us derive that in case of a sphere. Just a moment. Okay. Consider a long fluid column like this, which is vertical basically. And we have to consider gravity also in this situation. Let's say fluid density is rho, or rho L you can take. Let's assume it's a liquid and its viscosity is eta. Fine. Assume there is a sphere whose density is rho naught greater than density of the liquid. If density of object is more than density of liquid, definitely it is going to sink into the liquid. Okay. So suppose this sphere is released from rest in this fluid. Released from rest means initial velocity of the sphere is zero. Initial velocity, if it is zero, there won't be any viscous force acting on it. Can one of you quickly tell me what other forces will be acting on that sphere when it is just released?
Gravity.
Gravity. Any other forces?
Buoyant force.
Buoyant force. Good. Gravity, that is its weight, will be a constant force acting on it like this. And there will be buoyant force also acting on it in the upward direction. Since the density of object is greater than density of liquid, buoyant force will be weaker than the weight. Okay, so weight dominates and there's no viscous force acting yet. As a result, what will happen? There's a net force in the downward direction. This sphere will start gaining velocity in the downward direction. Okay, as it gains velocity in the downward direction, imagine the sphere at a random instant somewhere here. The same vectors, weight and buoyant force, will be acting on it. Since it's fully immersed, the same amount of buoyant force always acts on it. Okay, and of course, weight will also be constant. It will keep acting. And by now it would have gained some speed. Okay, gained some velocity in the downward direction. But the velocity is still small. Let's assume the velocity is still small, that the viscous force developed is quite weak. So now there is buoyant force, the green vector. There is also viscous force, the orange vector, acting in the upward direction, or maybe I should draw it in yellow for you to be able to see it better. Yeah. Okay. Green represents buoyant force, yellow represents viscous force, red vector, which is downwards, represent weight. Weight is still dominating. See, viscous force gradually increases now as speed increases. So for some time, weight will dominate. And if weight dominates, the net force is still in the downward direction. So initially there was large net force in the downward direction. Now there will be a smaller net force in the downward direction because viscous force is increasing. Fine. But as long as there is a net force in the downward direction, its speed will increase further. It will accelerate. It will speed up further. And if it speeds up further, then viscous force will continuously increase. Then at some time, okay, there will arise one instant at which weight is exactly balanced by the sum of buoyant force and viscous force. Okay, actually in the last problem when we solved that sphere question, we didn't consider buoyant force also. Anyway, let it be. Let's assume density of the liquid and sphere were equal in that case. So you didn't have to consider buoyant force. So weight, buoyant force will be acting and the viscous force will increase itself significantly because the speed goes on increasing, no? So there will come one instant where the net force on the object, on the sphere, becomes zero. If net force becomes zero, its speed becomes constant, its velocity becomes constant. That constant velocity that it attains is what we call as terminal velocity. Fine. Here we assumed density of the sphere to be more than density of the liquid. So it is sinking in the downward direction. It's attaining a terminal velocity in the downward direction. The same can happen in the upward direction also. Okay, suppose there's an object whose density is less than that of the liquid and it is immersed deep in the liquid and released. Since the density of object is less than that of the liquid, it will have a tendency to rise up. As it rises up, viscous force will act downwards. Okay, and after attaining some velocity, the buoyant force will be balanced by weight and viscous force. Then it will attain terminal velocity, a constant velocity in the upward direction. So terminal velocity can be attained upwards or downwards, depending on whether the object is denser than the liquid or lighter than the liquid. Okay, here we are considering it is denser. So consider this situation when it has attained terminal velocity. At that velocity, the sum of, okay, when velocity becomes equal to terminal velocity, means when velocity becomes constant, the sum of buoyant force and viscous force is balancing the weight. Okay, if you just write the equation for this, can one of you tell me what is the equation for buoyant force or the formula for buoyant force? Object is completely immersed in the fluid, and fluid is non-accelerated. Don't consider those cases of acceleration and all. Fluid is non-accelerated, object is moving, fluid is static only and non-accelerated. What is the formula for buoyant force?
So density of the liquid into G into volume of the sphere.
Density of liquid into volume immersed. Volume immersed is the complete volume of the sphere multiplied with G. Okay, that's buoyant force. Viscous force, you know, is 6 pi eta RV is equal to weight. Weight is density of object into volume 4 by 3 pi r cube multiplied with G. Okay, cancelling the common terms, one r gets cancelled, pi also gets cancelled. Pi and r, if you cancel, there will be an r square here. Pi and r, if you cancel, there will be an r square here. Anything else can be cancelled. 2 can be cancelled. So this becomes 2, this becomes 3, this becomes 2. Now you take LCM, rearrange and all. What is our aim? Our aim is to derive an expression for this V. Okay, the V here is Vt, terminal velocity. Only then this equation will be valid. So you get Vt is equal to 2 by 9 multiplied with density of, okay, object is denser than liquid. So density of object minus density of liquid into r square G divided by eta. This is the formula you will get for terminal velocity. Okay, vanilla for first year board exam, this is very important. I think one long answer question or maybe 4-mark question will be there based on this. Okay, so here we assume object to be denser than the liquid, we get this formula. If object is lighter than the liquid, then buoyant force will dominate. Then terminal velocity will be attained in the upward direction. Then how do we adjust the equation? If velocity is in the upward direction, weight and viscous force will be in downward direction. Buoyant force will be balancing them. So if you write equation that way, okay, see this equation we already derived is for downward terminal velocity. If you want upward terminal velocity, it's almost the same expression. You will just have density of liquid minus density of object. That's all. R square G divided by eta. Right. Questions based on this are quite common. They may give you densities, radius, everything and directly ask you terminal velocity, or ratio based questions. They can say two spheres are dropped. Their densities are in so and so ratio, radii are in so and so ratio. What will be the ratio of their terminal velocity? Such questions can be asked. Basically, it's a direct application of this formula. Okay. So this is all based on viscous force acting on a sphere, which is given by Stokes' law. So what are the factors on which viscous force on a sphere depends? It depends on viscosity of the fluid, size of the sphere, that is the radius, and the speed with which the sphere is moving through the fluid. And the formula is 6 pi eta RV. We solved one problem based on it and then derived terminal velocity also. Okay. Next thing is Poiseuille's equation. Uh, can one of you tell me what Bernoulli's equation helps you relate? Or just tell me the equation first. Bernoulli's equation. Okay. P or P1 plus rho G H1 plus half rho V1 square is equal to P2 plus rho G H2 plus half rho V2 square. That is Bernoulli's equation. And Bernoulli's equation is applicable only to ideal fluids. Ideal fluids are non-viscous. Okay. Ideal fluids in steady flow. You can use Bernoulli's equation. Fine. So obviously for viscous fluids, Bernoulli's equation won't be applicable. So if you want to find out the volume flow rate of a viscous fluid, through a narrow tube. Okay, narrow tube, sometimes they may also call it as capillary tube. Then you use Poiseuille's equation. Okay, it tells you what is the flow rate through a tube. And it's also important to note that the tube must have a circular cross section. Only for such cases, Poiseuille's equation is applicable. There may be other equations for other types of cross sections, but in your syllabus, you have only this case. Okay, let's visualize the tube first. Just a moment. Suppose, suppose there is a viscous fluid flowing through a tube of circular cross section like this. Now, see, I'm saying it's a viscous fluid. Definitely, there will be some resistance to its flow. If you want to maintain the flow rate, okay, if you want to keep a viscous fluid flowing with a constant rate, you should apply a force on it. Otherwise, due to viscosity, it will slow down and stop. So if you want to maintain the flow rate, you will need to apply a force on it. How do we apply force on fluids? By creating a pressure difference. So let's say the pressure here is P1 and the pressure here is P2. If the fluid is flowing to the right and you want to maintain the flow rate, can one of you tell me which pressure should be greater?
P1 should be greater.
Obviously, P1 should be greater. Only if P1 is more than P2, there will be more force from the left side than the right side and it will be able to move against the viscous force. Okay, so P1 should be more than P2. And greater the pressure difference you maintain, greater will be the flow rate. Okay, so volume flow rate depends on pressure difference. What are the other factors on which it depends? Obviously, it will depend on the radius of the tube. Greater the radius, greater the space for the fluid to flow, greater will be the flow rate. So it will depend on radius. Okay. It will definitely depend on viscosity of the fluid. Less viscous, easy flow. More viscous, difficult flow. Okay. It will depend on viscosity. Another factor on which it depends is the length of this tube. Why? Greater the length of the tube, okay, greater the viscous force it will have to overcome. Okay, because longer it flows, see, wherever it is flowing, it will be experiencing viscous force, no? So greater the length, basically there will be more area of contact between the layers. So there will be more viscous force acting between them. Okay. Therefore, the volume flow rate, which can be expressed like this, depends on pressure difference, delta P, also length of the tube. Now, there's a slight problem here. Radius and length have the same dimensions. If there are two quantities which have the same dimensions, you can't use dimensional analysis to derive a relation between them. Okay, you can't use dimensional analysis to derive how volume flow rate depends on all these. Okay, because there are two terms having same dimensions. But Poiseuille has solved that problem for us. Okay, what he found out is it doesn't depend on pressure difference and length separately. He found that it depends on something called pressure gradient. Okay, pressure difference per unit length. It depends on that. So we'll treat that as a single quantity, then viscosity and radius. These are the factor rate. Okay. Now again, using dimensional analysis, I want you all to derive how volume flowing per unit time. It's called pressure gradient. Okay. Next, coefficient of viscosity, and then radius. Do this quickly. Okay, left hand side, volume flow rate, volume per unit time will be L cube T power minus 1. Next, first term on the right hand side, pressure difference divided by the length. Pressure is force per unit area. Force is ml T power minus 2 divided by area L square. It will become like this, divided by L again. So first term on the left hand side is ml power minus 2 T power. We had derived already ml power minus 1 T power minus 1 to the power B. Radius is just L to the power of C. Balance the exponents on both sides for each quantity. You will see that A is equal to 1. Okay, the power of pressure gradient will be 1. B will be minus 1 and C will be 4. Okay, fluid through a narrow tube is proportional to pressure gradient. You can write delta P by L, you can write delta P by delta L, you can write dP by dL also, nothing wrong, into R power 4 divided by eta. Okay, and Poiseuille found out that the proportionality constant, okay, it has been determined experimentally, it is pi by 8. Therefore, volume flow rate of a viscous fluid through a narrow circular tube is pi by 8 pressure gradient. Fine. Problems based on this we'll solve in the next class. But This basically gives you volume flow rate of a viscous fluid. Okay. So you can't use Bernoulli's equation for viscous fluids. You can't use this equation for ideal fluids. Obviously, eta will not be there in ideal fluid. Fine. So next class, which is tomorrow, we'll just solve some problems based on this and finish this chapter. Monday onwards, we can start heat and thermodynamics. Okay. Thank you all. We'll continue tomorrow.
Thank you so